Thanks for watching this video. My name is Junyao. I am a PhD student at Stanford University. In this video, I'm going to tell you about our recent ITCS paper, Beyond the Worst Case, Budget Feasible Mechanism Design. This is joint work with my advisor, Aviad Rubinstein. Let me start by introducing the problem setup. In budget feasible mechanism design, there's a single buyer who has a budget B. And there's market I. There are n sellers in the market. Each seller has an item, and the item has a value V and a cost C. Value V is public information, which is known to the buyer, but the cost C is private information, which is only known to the seller himself. For example, here we have a fish market, and the buyer, who is a chef, he knows the value of the fish from his experience, but he doesn't know the true cost of this fish to the seller. The goal of the buyer is to procure the items from the market in order to maximize his total value. Moreover, we make a large market assumption, that is, the cost of each item CI is at most little o of B. The goal of budget feasible mechanism design is to design a mechanism that decides which subset of items to purchase for the buyer, and specifies the payments to the sellers. A mechanism has to satisfy two constraints. First, the sellers should be incentivized to honestly report their costs. Second, the total payment to the sellers has to be within the budget. Note that if both value and cost are public information, then this becomes the classic knapsack problem. Instead of formalizing the precise definition of a mechanism, let's just do an example to give you a better sense. For simplicity, let's assume every item has the same value but unknown cost. Consider the following mechanism, which is called clock auction by installer and JIB. First, we initialize an offer P to be the budget B, and we initialize the number of remaining sellers M to be the number of sellers N. As long as P times M is above the budget B, we decrease the offer P slightly, and we ask each remaining seller to leave if their cost is above the offer. And we update M. We continue doing this until P times M is at most the budget B. At the end, we pay each remaining seller P and give their item to the buyer. It's easy to check. The sellers are incentivized to behave honestly. Specifically, if at any point during the mechanism, the cost of a seller is above the offer, then there is no incentive for the seller to stay, because even if he stays, there is no way for the final payment to be able to cover his cost. Moreover, the total payment is always within the budget because of the while condition. Now we have seen an example of a mechanism, but how should we grade the performance of a mechanism? Recall the problem instance is specified by a budget B and a market I, which consists of the values and costs of the seller's items. If both values and costs are public information, then we can think of I and B as an instance of knapsack problem. Therefore, a standard performance measure for mechanism is worst-case competitive ratio. The worst-case competitive ratio is the value achieved by the mechanism on the instance I and B divided by the optimal value of the knapsack instance I and B. And both I and B are chosen by the adversary. The clock auction, which I explained a couple slides ago, achieved a 1/2 worst-case competitive ratio. And a nice result by Anari, Gowell, and Nixad shows that there is a mechanism that achieves the 1 minus 1 over E worst case competitive ratio, and they prove 1 minus 1 over E is the best we can get. This worst case optimality result is very nice, but does worst case optimality indicate that the AGM mechanism is a better mechanism for practice? Unfortunately, we find worst case optimality doesn't generalize to typical case. Consider the following extremely simple instance. There are n items. They all have the same value 1 and the same cost 1. The buyer's budget B is equal to n. For this instance, it's easy to check the clock auction will converge to a payment 1, and it extracts the full value of this instance. However, it turns out the AGM mechanism only extracts a 1 minus 1 over E fraction. You might say this instance is too special, but consider the following more realistic instance. There are 1,000 items. They all have the same value, but their costs are sampled from a natural distribution, and we fix the budget to be 20,000. The following table shows the expected fraction of the full value which AGM mechanism and the clock auction achieve respectively for various cost distributions, such as Gaussian distribution, uniform distribution, exponential distribution, and Gaussian mixtures. We can see that for all these distributions, AGM mechanism consistently get close to 1 minus 1 over E fraction. But the clock auction can do much better. Therefore, it's natural to ask, can we get the best of both worlds? Is there a mechanism that not only is worst case optimal, but also performs favorably on every instance? By perform favorably on every instance, I mean the mechanism has to be as good as a large class of mechanisms on every instance. But which class of mechanisms should we consider as a benchmark? At least we want this class to contain clock auction and the AGM mechanism. The most ambitious class is obviously the class that contains all the mechanisms. In the next slide, I will explain it is unreasonable to compare to some non-uniform mechanisms. So we will compare to all the uniform mechanisms for now. Informally, a mechanism is uniform if every seller is facing essentially the same distribution of offers. For example, in clock auction, essentially every seller is facing exactly the same offer, which is the payment that clock auction converges to in the end. And the AGM mechanism is also a uniform mechanism. In this slide, I want to explain why it is unreasonable to compare to all the non-uniform mechanisms on every instance. First, let's fix an arbitrary contrived market I prime that consists of values Vi prime and costs Ci prime, and consider the following non-uniform mechanism. This mechanism ignores the actual market I it is facing and only takes the buyer's budget B as input. It first computes the optimal solution to the knapsack instance that is specified by the contrived market I prime and the budget B. Then it offers each seller I in the knapsack optimal solution a take it or leave payment Ci prime. Although this mechanism is silly because it doesn't care about the actual market I it is facing, it's trivially truthful and budget feasible. And there is no way we can compare to this mechanism on instance that is specified by I prime and budget B. Now I want to state our first main result. We design a randomized mechanism that is almost as good as any uniform mechanism on every problem instance. Moreover, we examine our randomized mechanism in the same empirical setting as before when we compare the AGM mechanism and the clock auction. Namely, the items have the same value, but the costs are sampled IID from natural distributions. The results are in this table, and we can see that for single model distribution, both our mechanism and the clock auction outperforms the AGM mechanism by a large margin. And on multimodal distributions, our mechanism outperforms the other two mechanisms significantly. Our mechanism is very simple. For simplicity, let's again assume every item I has value 1, but an unknown cost. An important notion that's used in our mechanism is lottery. Specifically, a lottery L with parameters P1, P2, and T is a distribution over 2 take it or leave offers. Namely, we offer the seller a payment P1 for his item with probability T and offer P2 with probability 1 minus T. Our mechanism is as follows. First, we partition all the sellers into 2 buckets, X1 and X2, uniformly at random. Then, we ask the sellers in X1 to report their costs and compute the best lottery that achieves the highest expected value on X1, such that the expected total payment is bounded by B divided by 2. Similarly, we ask every seller in X2 to report their cost and compute the best lottery L2 that achieves the highest expected value on X2, such that the expected total payment is bounded by B divided by 2. Finally, for every seller in X1, we sample a payment from lottery L2 and offer it to the seller. We keep doing this until we spend B divided by 2. And similarly, for every seller in X2, we sample a payment from the lottery L1 and offer this payment to the seller. And we keep doing this until we spend B divided by 2. Later, I'll show the proof outline of the optimality of this mechanism against any uniform mechanism. But now I just want to say this mechanism is simply truthful because for every seller, the lottery they are facing does not depend on the cost they report. Therefore, there is no incentive for them to cheat. And this mechanism is simply budget feasible because of the constraint in the third step. So far, we have seen that worst-case optimality doesn't speak for the average case performance. And as I explained before, instance optimality is too much to hope for if we want to compare with non-uniform mechanisms. Therefore, we proved our instance optimality result against the uniform mechanisms. Now, we strike a reasonable middle ground where we can compare average case performance with non-uniform mechanisms. Specifically, we study a semi-adversarial model called budget-smoothed analysis, which was proposed in our last year's ITCS paper. In budget-smoothed analysis, the market I is worst case chosen by the adversary, but the budget B is sampled from a random distribution. Now let me introduce the model of budget-smoothed analysis. First, we fix a budget distribution D, for example, the empirical distribution of buyers' budgets. Then, the adversary picks a single worst-case market I. Arguably, there are many buyers procuring items in the same market, but they have very different budgets. Then, we sample a random budget B from the distribution D and run the mechanism on the instance that is specified by market I and budget B. The performance measure for a mechanism is its expected competitive ratio, where the expectation is taken over the budget distribution D. Notice that once we fix a budget distribution D, then the budget smooth analysis is essentially a maximum game between the mechanism designer and the adversary, where the objective is the expected competitive ratio. First, the mechanism designer chooses a best mechanism M, and then the adversary chooses a worst-case market I. We have the following results for budget smooth analysis. First, we prove that our randomized mechanism is optimal in this model, regardless of the budget distribution. Moreover, we give a characterization of the worst-case market for any given budget distribution. And we show that our randomized mechanism has better than 1 - 1 over E expected competitive ratio for any non-trivial budget distribution, regardless of the market. By non-trivial, I mean there are at least 2 budgets in the support of the budget distribution. In contrast, given any bounded range of budgets, we can construct a single market where AGN's worst-case optimal mechanism only gets 1 - 1 over E competitive ratio for any budget in the range, which shows a separation. Finally, we prove a robust hardness result that says no budget distribution allows better than 0.854 expected competitive ratio for the worst-case market. Finally, I wanted to give an overview of the proof of our main results. First, I wanted to talk about the instant optimality result against the uniform mechanisms. Here is a brief proof outline. So first, we prove that for every instance, the optimal uniform mechanism is a lottery of 2 take-it-or-leave payments. This is by using a greedy exchange argument. Then, we prove that our randomized mechanism can approximate the optimal uniform mechanism arbitrarily well. This is basically applying concentration bound in a clever way. Now I wanted to talk about the optimality of our mechanism in budget smooth analysis. Recall that given any budget distribution D, budget smooth analysis is essentially a maximum game between the mechanism designer and the adversary. Once we apply the min-max theorem, this is equivalent to the following min-max program. Given the min-max program, we first analyze it with the restriction that the mechanism M is a uniform mechanism, and we give a characterization of the worst-case market I star of this restricted min-max program. In I star, items have equal value, and the CDF of their costs satisfies the following property. We denote the CDF of worst-case market I star by f of c, and we draw the plot where the x-axis is f of c and the y-axis is c times f of c. We prove that this curve must be convex. In the second step, we show that by convexity, non-uniform mechanism is no better than the uniform mechanism for the worst-case market I star. Since we have shown that our mechanism is instance optimal against the uniform mechanisms, it follows our mechanism is an optimal mechanism in the restricted min-max program from the first step. And by point 2, our mechanism is also optimal in the original min-max program when we bring back the non-uniform mechanisms. This proves the optimality of our mechanism in the budget smooth analysis model. That is all I wanted to tell you. If you have any question, feel free to reach out to me using email. And if you are interested in budget smooth analysis and wanted to know more about it, please check out the video of our last year's ITCS paper, which is also on YouTube. And finally, thanks for watching this video.